All right, so let's see if we can figure out this action-reaction pair. All right, so car, and we'll make it like a beetle, so it's kind of crunchy, all right? So car, the windshield of the car, so I'll put force car, and then the bug, force bug. So if action equals reaction, this is true, right? But it certainly doesn't seem that way. It doesn't feel like they're equal and opposite because the bug dies. And it's not like when the bug hits the windshield, you're like, whoa, when it hits the windshield, right? You didn't really notice other than, oh, dang, I got to clean the windshield now. So what is it that, if this is true, which it is, then what is it that makes it so hard for the bug, and other than a slight inconvenience for you, you're going to survive? Cam?
Car is heavier.
Yes, that is correct. So now we're going to institute Newton's second law. Newton's second law says F equals ma. So the force that pushes on the car and the force that pushes on the bug, same thing. Let's substitute ma here and here. So mass of the car times the acceleration of the car equals mass of the bug times the acceleration of the bug. Cam said the mass of the car is much bigger, so let's adjust this, right? Mass of the bug, teeny. So in order to make ma equal ma, how are the accelerations?
Bug's going fast.
Yeah. So what you feel, remember, you have all these accelerometers in your body, is you feel this. Is that very big? No. Minimal. The bug feels this. This is change in velocity. Think about it. Bug is flying along, everything's fine. Well, bam! He has to decelerate, stop, turn around, and go the other direction, which potentially could be a pretty big, it's a life-altering change in velocity, right? You know what the old physics joke is? Not the fall that kills you.
Oh, yeah. I saw this picture on Twitter.
Yeah, it's like sudden change of velocity at the bottom. I've never thought that was funny. I don't know why that's like a joke even at all. True?
Well, what if the bug's just standing still? Or, I mean, like flying in the air.
Like hovering like a little
Yeah.
mini bug helicopter?
Yeah, like in the exact same spot
Uh-huh.
when the car hits it. It's still the same thing.
Yeah.
It has to go from 0 to 70.
A very short time. It's the delta T that really kills you. Okay. We're going to talk about this. We're going to talk about collisions in the next unit and how the time through which an object changes its velocity is really the kind of critical piece. Think about all the safety devices that we have in cars. It's all about extending contact time. Okay. You ever hear about like drunk driver gets in an accident, kills a family of 4, he walked away? Yeah, because he was relaxed. So, here's the rule. If you have an impending collision, you should relax. All right, let's talk about skydivers. Skydivers, so our skydiver is going to jump out of a helicopter, okay? Our skydiver steps out of the helicopter, so he has no horizontal velocity, steps out of the helicopter, and has an initial velocity of 0, okay? So for one moment, he's sitting still. Just for a moment. So if he's sitting still, now we need to draw the free body diagram. We've got to draw all the forces, all the vectors, sum of forces on the skydiver. So what are the sum of forces right now at this moment? Gravity. Anything else?
Weight.
Well, gravity is his weight, so it's mass times gravity. That's how we turn it into a weight. Sam? Yeah, I used a helicopter instead of a plane, so there's no horizontal velocity.
Oh.
And we're gonna pretend like there's no backdraft or anything from the helicopter. It's a very magical helicopter. So the only reason for we could make this like a really, really, really tall tower too. The only reason for the helicopter is to make this vertical only in orientation. So if this is the case, if that's it, so we've got gravity pulling him down, then what is his acceleration at that moment? 9.8, that's correct. So his velocity is 0, but his acceleration is negative 9.8. Okay? A little bit later, he picks up some speed. Whee! Okay? Did he get fatter too? Yeah, he also got fat. That's just due to air resistance. So like his coach billowed. Yeah. Stress eating. He's stressed. He had a little snack on the way down. Has his weight changed? No. So that vector is still the same. What's changed? Yeah, the velocity. So the velocity here initially at the moment he stepped off the helicopter was nothing, but now it's something. Velocity equals something. Okay? So his velocity is greater than it was initially. And somebody said there's air resistance. There is drag air resistance in this particular case. Yeah. So I'm just going to go like this, drag. Okay. What's the acceleration like here?
9.8.
Is he still accelerating at 9.8?
No.
Now look, just if we weren't worried about anything, if we see here, the force is mg, so the acceleration is 9.8. Now the force is mg minus drag. mg hasn't changed, so what does that tell you about his acceleration?
A little bit less.
A little bit less is correct. Sam, did you have a comment? Okay. A little bit less than negative 9.8. So this is interesting because his acceleration has actually gotten smaller, right? But his velocity is larger. So he's falling faster, but as he's falling, he's not decelerating, he's accelerating at a lesser rate, right? Okay. A little bit later, falling, faster and faster, even faster, woo! Really fast now. Oh, and one leg got longer. So has his weight changed? Nope. As he falls faster, so velocity is really fast now. What happens to the drag?
More drag.
Yeah, it gets bigger. What would happen, so I'm going to make this vector longer. What would happen if drag was so big that it was equal to the weight? He would float. He would reach terminal velocity. He would, well, yeah, what if they're equal, what does that mean for motion?
0.
No more acceleration. Constant velocity. Does he stop is my question. No, he doesn't stop. He reaches, you're correct, really fast, and it's called terminal velocity. It means that you can't go any faster. A couple of years ago, maybe it's a little more than a couple of years ago, Red Bull sponsored a guy trying to doing like break the speed of sound, right? Yeah. What did this guy have to do to be able to, with a human body, to break through the sound barrier? Jump from space, basically. That's correct. So he went up in this big like weather balloon type thing outside the Earth's atmosphere. So really, really, really high. And the reason for that is to reduce drag, right? Because drag is based on the shape of the object, how fast it's moving, and the viscosity of the fluid. Yeah. So if you can go to a really low density fluid, you can go really fast. You don't have as much, drag, air resistance, fluid resistance. So he went almost outside the atmosphere, jumped, was able to speed up so that by the time he hit the atmosphere, when this happened, he was going faster than the speed of sound, faster than like 800 miles an hour, really fast. Okay? So this terminal velocity for normal skydivers is in the neighborhood of 250 miles an hour. It's fast. You wouldn't want, so he can't fall any faster than this, and if you hit the ground at that terminal velocity, most likely you will die. There was an example of a woman who survived, and she landed on asphalt. Oh, I know. She landed on asphalt. She did survive, and it broke like every bone in her body. The amazing thing was, she was pregnant at the time.
Did the baby break the bone?
Did the baby? Yeah, she wasn't big pregnant. She didn't know she was pregnant, so it was very early term, probably she was 6 weeks pregnant. Baby survived and was fine. Yeah. The uterus is an amazing thing. It's like got a little built-in airbag or something, 'cause yeah, the baby was fine. Yeah. So everybody survived it, but yeah. And she landed face first. Yeah. Very different after all the plastic surgery. She actually had tons of plastic surgery. She broke like no parachute. Yeah, no parachute. She had a parachute, but they both didn't. I believe the backup parachute deployed, but it didn't open, so it did reduce the speed of her fall. I don't think she quite hit it 250 miles an hour, but all right. So let's talk about the parachute. So if this guy is probably not going to survive if he hits the ground at normal terminal velocity, about 250 miles an hour. Okay. So to combat that, he will open a chute. Okay. And the chute hasn't quite billowed yet, all right? So it's kind of, in the process of opening. Got it? So what will that change? Drag, right. So mg will stay the same. His weight is the same. But because of all this extra stuff dragging through the atmosphere, drag will be huge, right? And have you ever seen, so drag is way bigger than the weight, right? Have you ever seen video footage when somebody opens their parachute? What happens? Yeah, they get like slingshotted back up, right? You've seen that? Yeah, that doesn't really happen. Think about it. Yeah, it's a relative thing. If you went from 250 miles an hour, like, yay, woo, free fall, to any speed up, what's the delta V there going to be? A lot. You might as well just go from 250 to right? You're more likely to survive that delta V, that change in velocity, than 250 down to anything up. So what's happening there? Why does it appear like when they pull their chutes that they're
well, because your brain's following their motion down if you're watching it, and then when they deploy the parachute, they slow down and your brain's still in the same,
So your frame of reference is falling with them at terminal velocity.
Yeah.
Whose perspective are you viewing it from? The camera person, right? So the camera person's also skydiving, and unless they magically can pull their chute at the exact same time, they're continuing to fall. The person who pulled their chute is also falling, but not as fast. So from the frame of reference of the cameraman, it looks like they get jettisoned upward, but that would be bad. Your organs would hit your skeleton at such you'd just be scrambled. So, yes. All right. So now what happens is,
You get accelerated.
yeah, velocity is a lot less than terminal velocity, right? So you slow down because of this. That's a less than symbol. And what's the acceleration?
Negative.
Yeah, the acceleration if negative was down, the acceleration here,
Still negative. No, quite positive.
the negative, it's actually positive. So the acceleration is positive, which means deceleration. You're still traveling downward, but your acceleration, it's like hitting the brakes. If you hit the brake, friction pushes your car backward, right? But you have to stop before you can go backward again, right? So that's what's happening here, is the skydiver is decelerating. All right, eventually then, the parachute opens, right? And mg is the same, so I'll just write it over here. Mg is the same. And what's drag? Is it really, really big here? Because of the big surface area? Yeah, initially, but eventually what happens is drag actually reduces so that it's equal to the weight again. Why? Why are they equal again? Sam?
Because the drag continues to be bigger than the mass times gravity when they eventually start going up.
Yes, that's correct. So if this continued to be true, eventually drag would win, right? And there would be no hitting the ground. You would just like go upward. Since he's slowing down, what effect does that have on the drag? The slower you go,
The drag.
that's right, the drag decreases until we reach a new terminal velocity. And this terminal velocity is survivable. The new terminal velocity, they say when you're training, is similar to if you were to hit the ground jumping from about 6 feet. And so a lot of skydiving schools have you like jump off a ladder or a 6-foot high and like learn to make, because you can like sprain an ankle or break a leg or, you know, from a 6-foot jump, right? So they just try to teach you how to take that impact so that, yeah, like to run or to roll or that, yeah. And you know that now sort of the standard is if you're just going to do a quick skydive jump is you actually like buddy skydive. Have you seen that?
Yeah.
Where you skydive with an instructor and they kind of take care of the whole landing part. Okay. Jerome?
Is it possible to have a force of 0 right when you land, or?
Well, this is net force of 0. So, yeah.
So, I mean, like, you're taking like a step when you land, like you don't feel anything.
Probably not, but certainly not your full weight, if that's what you're asking, yeah. Yeah, because of the parachute helping you out. Okay. So, hopefully, if you were to see questions on the test about skydivers, you would be able to answer it. This is just conceptual.